Okay, let me go back to where I was. So like I say, I want to focus towards the end on talking about projects and, helping you guys get your proposals together. But the main focus of today is on curve fitting, which is the technique used to derive all of these coefficients that get used in all of the models you've done so far, which we haven't talked about. Bless you. So that's kind of where we're headed. I did want to do, before I talked about curve fitting, I wanted to do something that we did earlier in the class, which is a little bit of practice with formulations. So what I'm going to do, well, actually, let me first, we'll do the formulations first. Okay, so I want to give you some scenarios, and I'm asking you, and I'll have you work with whoever you're most immediately adjacent to in thinking about this. I want to ask you, which of the basic formulations that we've used would be most appropriate? Do you think would be most appropriate for these particular scenarios? And why would you use those? How do they make sense out of this? So this is a bit of priming to begin thinking about deriving coefficients. That's why I want to do this, doing curve fitting. Okay, so let's say someone is chasing you and we're considering how fast you run as a function of how close the potential attacker is to you. So not a great scenario, but these things happen. Yeah, I'm gonna give you a second to think about that. So just spend a second thinking about it and then chat with your neighbor, if you were to choose like a way of formulating this, what would you choose for that? What would you choose as a modeling equation? So think about it for a second and chat with your neighbor. Yes, so go ahead and talk about it.
Okay, really cute dog. You're gonna build up speed and then you're gonna reach the mountain and then you're gonna go like that for a little while and then you're gonna get high and you're gonna slow down. And then might be like a little bit of
So again, think about the basic formulations. Which of the basic formulations would you use for this? Not what would it look like, but what formulation? How would you formulate that? I'll say there are probably, I think, two of the basic formulations that you might argue might fit this one. Two ways of thinking about it. Yeah, so talk through the formulations we've worked on and see which ones seem to fit.
Yes, I think that works. It's like depending on. Yeah.
We've got mass action, we've got gradients, we've got hyperbolic saturation, we've got first order growth and loss, we've got second order growth and loss. I think I said gradients already. We've got logistic growth. All of these are possibilities. Which one is the best analog for this is the question. All right, you guys have a firm idea, or are you just confused? Which one? You guys got it. Okay, what do you got for an idea? Share what you got. So your rate is dependent on how you're looking at, you're thinking of a gradient equation. That's what you're saying. And that what would be the analogs of the concentrations of the two reactants is, I guess, what you'd want to be asking if you go back to sort of chemistry, like how would it work? Like how does that play out is I guess what I'm asking you. If you're using gradients, what's the analog of, the concentrations of two?
We're talking about like the rate of speed of the attacker versus like the rate of speed of you.
Right.
And how that fluctuates depending on the distance between you and the attacker.
So if it fluctuates based on distance, are you thinking about it so you're thinking of this as a gradient, yes? So you're thinking in a gradient equation, it's like how big a distance, the flow is proportional to how big a distance is. The bigger the distance, the more the flow, right? With a gradient, the larger the gradient, whatever the gradient is. So what would be the gradient in this situation if that was? Okay, well, we're just getting ideas out here. Someone else have other ideas? Yeah.
You kind of had two, but the one I was leaning towards is like the Voltaire kind of, because I feel like it's kind of similar as in like it's part of the brain-esque a little bit, because like some speed, but also like as their distance from you would decrease, your speed would increase because they're closer, and then when you get far enough away, you start to slow your speed down because either you're tired or because you have more distance, and then you would start to make up like speed or make up distance kind of.
Right. So Volterra fundamentally is a variant of mass action, where you've got these concentrations of predator and prey. And so what would be the analog in this particular scenario? What is this sort of analog of number of predator and number of prey? Because that's always, when you think about these, it's getting dark up there. I'm going to turn the light on. When you think about these, sort of like analog, when you're trying to figure out what's the what's the right, basic formulation. You want to make sure you're kind of thinking through all the way down the line in terms of, okay, what's the analog? See, mass action is based on this idea of like chemical concentrations. What's the analog of that? Or you can give it a sort of number of predator and number of prey, whatever. It's the amount of stuff in two compartments. So you want to, if you're going to think about that as an analog for this, you want to make sure as you think about this, you can say, okay, the equivalent of, concentration or the equivalent of density or predator and prey is what in this model? Because that's what you need to think about, because that's the point, is you're trying to think about what's the analog, how does that equation fit this particular situation?
I would think the number of predators would be like analogous to like total distance between you and the person chasing you, and then speed would be analogous to, I guess, number of prey, if it fit in with that.
Those seem kind of different to me, because one is like a rate, the speed, and the other is you know what I'm saying? It's like, the predator and prey they're both the amount of stuff. And that seems like you're like in that situation, one is a rate and the other is a distance. Is there to think these things through when you're thinking about analogs, and this is going to be really important for your models too, thinking about your modeling projects. What's the real analog for what you're doing? What basic formulations are going to drive your model? So let's keep going with some other thoughts here. Yeah.
We were talking about the Michaelis-Menten equation as we applied it to the photosynthesis problem, and thinking about that as an analog, because you have like the distance from the attacker as a stop potentially, and then like the flow would be like the rate at which you were running away from the attacker and like distance per time. And then that flow is dependent on a lot of things, like the level of your adrenaline, how close the attacker is to you, because you're probably going to be running a little bit faster if they start to catch up, the amount of like potential energy that you have stored, and like how quickly you can convert that into kinetic energy.
Right, and also implicit in what you're saying is this idea that there's probably some maximum speed at which you can run. So your proximity is analogous in your thinking here. Your proximity is analogous to effectively your substrate concentration, or your amount of light energy, or your amount of nitrogen, or your amount of whatever it is that motivates you. If that's really small, you're thinking about that as being kind of like distance, so that if the person's very far from you, you're probably not running at all, because it's a very low substrate concentration. It's a very low light energy, right? And then as it comes closer to you, it's like effectively a stronger concentration, and you're speeding up. But your capacity to speed up is saturating at some level, and you run as fast as you can. And increasing or decreasing the distance isn't going to, at that point, result in faster running, and maybe even at some point you have what we talked about, which isn't actually built into Michaelis-Menten, but we talked about it, an inhibition part where you're just so scared you're not even functional anymore. You're actually maybe even slowing down in the way that light, and the way that photosynthesis might slow down at extreme levels of light, because you're just not able to perform anymore. So that's definitely one basic formulation, which I think is probably a pretty good analog for this. So it's a saturating phenomena. You can as they come closer, again, analog, their closeness to you, analog of substrate concentration, you're running faster and faster until you just saturate. You can't go any faster. What other? So I like that one. That one I think you can talk about the pieces and parts as being fully analogous. Your running speed is analogous to rate of photosynthesis. Your substrate concentration is analogous to how close this person is to you, which is driving your fear level. So you could even think of fear as your substrate in this, more fear because of lower proximity, means faster running until you just can't run any faster. You're there. What is there another basic formulation which might also work for this? Are there other, because we've said that basically, obviously people have some maximum capacity to run. What other models have we looked at where essentially things eventually didn't get bigger? They got bigger and then they didn't get bigger. Which of our other basic model formulations had that property? Yeah. Logistic is another one. It's a different pattern. What's different about the shape, for instance, of logistic from hyperbolic saturation or Michaelis-Menten? Same difference. It's right. So it's a little different in the sense that it's something that builds on itself. The population has initially kind of an exponential increase in its growth rate, and then eventually it achieves a carrying capacity where it doesn't. So how could we make that one? How could we make this? So in that particular one, we're usually talking about a population which has some size to it. How would we make the analogs work in that, I guess, is the so our main parameters are in there. We've got an R, a growth rate, we've got a carrying capacity, or a maximum number. How would we make that analog? How would we think about the pieces and parts of this to make that particular analog make sense out of this? Well, in that case, we're talking about a population. So it's kind of in that one, we're graphing a stock. So in that one, you kind of have to think about speed as almost a stock, the rate of running as being like something that can accumulate. So it's a little bit different way of framing and thinking about it, but something that can accumulate, and there being sort of initial, when you start to run, as the population increases, you begin to run faster, but then eventually you're kind of limited by this second order loss, because as you run, you're sort of, I guess, running out of speed. Point being that it's a different way of conceptualizing the problem in order to sort of make the analog work in your mind. And when you're thinking about your modeling projects, you really do want to go through this process of thinking about what are the basic modeling formulations that could potentially apply to my given problem, and which ones actually make the most sense, which ones make the most kind of mechanistic sense, that I have the best that I can make the most logic out of when I'm thinking about that. It's a difficult thing to do, but it's a very important thing to be able to do. Let me throw up another. Yes, go ahead.
Before we close out on that example,
yeah,
I
sure.
wanted to say that it, as an example, kind of sucks. It's a little distressing to think
Yeah,
about,
no.
and it detracts from the lesson that it's trying to.
Yeah, I gotcha. I should probably do like a gazelle or something like that. I mean, a hunting, an analogy of an animal being something like that, because I agree with you. Right, I grant you that. It's yes, I got you. Yes, hear you on that one. All right, let's consider another one here, which is how fast water flows out of a bathtub drain as a function of the depth of water in the bathtub. So think through, our basic modeling formulations and chat with your neighbors, and let's come up with a thought on that one.
if you make all of it, there's like multiple names for it.
Yes. Yeah.
So think through the suite of different basic formulations and which one is going to be the best model of how fast water flows out of a bathtub as a function of depth of water in the bathtub. All right, anyone want to throw out a thought on this one? Yeah, go ahead.
Would logistic decay make sense? Because like it starts flowing quickly because the pressure is high and it goes down to the water stored. The lower you goes down, and then when the water starts to go.
Well, logistic is that S-shaped growth where a population grows by first order and then it loses by second order. So I think your description is actually combining a couple different formulations we worked with.
If it was logistic decay, would that make sense?
First order decay? Because usually when you say logistic, you're thinking about, you know, S-shaped and S-shaped growth sort of phenomena. Other thoughts? Shantanu, what were you guys thinking of?
We're kind of, again, looking at gradient. We were looking at the Darcy's example. But at like the first medium, I guess, to refer to the grade.
Right, so you're thinking of the depth of the water as essentially being the gradient. The higher the water level, the stronger the gradient. And so you're saying water flow is proportional to the depth of that. And it's actually similar to what Francis just described, right? So it's as the water goes down, the water goes down fastest when in this situation? When it's highest. And as it flows down, you're getting a decay as you said. So you guys good with that gradient? Okay, let's try another one here. Okay, so you've got like a singles bar, and it's the chance of people meeting each other and connecting with each other, and forming some sort of a relationship from meeting each other.
Yeah.
There's not many other.
Yeah.
All right, ideas. Maybe I'll start here. We'll go this way. Justin, what thoughts on this?
When we're talking about the disease model,
How would this function as a disease model? So go ahead and what is
we just got this, like,
it's
idea.
what is the category that the disease model falls into? What's the general category it falls into?
Like singles for like.
Well, I get that, but what do we call that? What's the name we use for because the disease mass action. So you're suggesting a mass action phenomena, and in mass action phenomenon, what's the sort of basic components of a mass action situation? Like, what's the generic situation of mass action? You go ahead, Shannon, yeah.
Two stocks, I guess. Two stocks that like affect each other, I guess.
You've got two stocks that are interacting, and the more of either stock there is, the faster the thing is happening. It's proportional to the product of the two stocks. And so you're suggesting that the more people there are in the bar, the more likely they are to sort of interact and, you know, connect with each other. Just like a disease or like, you know, addiction for that matter, for that model, that, you know, the interaction, the strength of the interaction is going to be a function of how many people. If there's no one there, there's not going to be a lot of interaction. Now, you know, obviously it might not be a perfect analog for that, but yeah, it's a decent analog for that. Okay, let's try another one. How fast people progress in acquiring a new skill as a function of how skilled the people are around that person.
Yeah.
So they got, yeah.
All right, maybe I'll start on this side. So sort of just the last time, Sadie, you seem to have an idea quickly. What are you thinking about here? Okay, you're thinking like, so what are the pieces of that there? So what's the equivalent of substrate concentration, and what's the equivalent of P max, I guess?
I feel like the equivalent of P-max would be like the amount someone, like the maximum amount someone can learn a new skill. Like, I guess maximum speed someone can learn a new skill, I guess.
Okay.
And especially just because like a function of how skilled the people around the person. So kind of having that as the, I'm sorry, I'm blanking, but like it's not being the person's like ability in the skill, I guess. And then the growth of that is affected by people around them, their own skills, their own ability to learn new skills. Does that make sense?
I think it does. You said a bunch of different things, but so let me try to put together some of what you said, because I think at one point you said there's probably a maximum rate of learning, and that's the equivalent of the P max. They can't learn faster than that. And the substrate is related to how different their skill is, their skill is from, or it's just related to how skilled the people are around them. That's essentially the substrate. The more skilled people are, the faster they learn. But at some point, they can only learn so fast. So, like I go to this music camp sometimes, and I have like these amazing musicians around me, and I'm learning a lot from them. But like my capacity to learn is going to saturate at some point. So, they could be the best musicians in the world, and I would only learn so fast from them. So something like that. Okay, cool. Any other thoughts on that one? Other ideas on that? I really like that one. Yeah.
I kind of thought like the law of cooling, but the law of cooling works for like heating too, right?
Sure, that's a gradient. The law of cooling is a gradient equation. So you're thinking of a gradient equation. So what's the gradient driving here?
Would be like skill level, technically, I guess, would be like your skill level, I guess, it would be
right.
Going down, going up, could be like their skill level minus your skill level.
That's the gradient. Yeah,
Because as you learn more, your skill, like as you get more skilled, it's gonna be harder to increase your skill level, it's gonna be more challenging.
or less to learn from them because their skill level is similar to yours. At some point, when you have the same skill level, you don't have the strength of difference. So I really like both of those. I think both of those are great. You know, they're different models. One assumes a saturating level. So there are different ways of thinking about it, but I think they're both very kind of perfectly legitimate ways to think about the way learning might occur. It might be just a result of the raw difference in skill, and the more difference there is, the faster you're going to learn. Or it might be that difference between that skill level of the trainers is going to increase your rate of learning up to some point where you just saturate and you can't learn any faster than you are. So both of those seem like perfectly legitimate alternate ways of thinking about, of using our basic formulations to conceptualize how we might model something. Okay, I'll just do one more here. So this one is the population of termites living on a log that has fallen in the forest. So you've got a log that falls, and termites come and invade it. How might we think about modeling that?
Yeah, I think it.
Well, I was. What was the specific model?
All right, anyone want to throw out a thought on this one? Yes. Right. So you have a loss from what's the model that seems like that we did that seems like the best analog for this? Right, the tortoises, where they have a finite value and there's a population growing on them, and the rate of growth of the population living on that is the inflow is proportional to the size of the stock of the resource. And so they're growing very rapidly, but they're depleting their resources as they go. You guys were on that too? I guess you, okay, cool. All right. I had a couple more examples here, but this is good practice for you guys as you think about your modeling projects, because you're going to need to make those decisions about, for each component of your model, what basic formulation are you using to drive your overall activity? Okay, so let's talk a little bit about the modeling projects. So here are our modeling groups as they stand. As you guys know, you've got a draft of your proposal due today, and your task for the remainder of today is to finish your modeling proposal and get it in by tonight. But you guys are then going to sort of critique each other's proposals before next Thursday's class. And that's sort of like the criteria you're going to use is sort of described in the assignment. But that's where we're going. We're going to get a chance to spend a little bit of time discussing the project proposals, giving you guys additional feedback before a final version of your project proposal is due on the 5th. So you're going to get quite a bit of feedback, is my point. on your modeling proposals. But I want you to enter that really thinking about what are the basic formulations that sort of govern the particular stocks and flows. So what are the stocks and flows, and what's the nature of the relationship between those stocks and flows in the models you're proposing, and how are we going to approach doing that? So that's kind of where we're heading in terms of those those projects. Yes. Any questions? Okay. All right. So we just talked about, these sort of basic formulations. The thing about all of these basic formulations is something that we haven't talked about yet is every one of them has coefficients involved in them. Every single one of them has, an R, a K, some sort of factor, an IK, some sort of a set of coefficient values that we've just been kind of using. And so what we're going to do for the remainder of today, or most of the remainder of today, is talk about how do people come up with those numbers, those coefficient values that are used in equations. And I want to give you some experience today in sort of deriving those coefficient values. So I did, for the preceding model, have you guys sort of look in the literature, because for many of us, that's where we get coefficient values from. If we're interested in modeling a particular phenomena, we understand other people have probably modeled that phenomena. We look in the literature and we see if we can find, half saturation constants or P maxes or whatever for similar, whatever the organisms we're working on or the particular, situations we're working on. We look in the literature to see if we can find some reasonable values. But even then, there's the question, where did those people get those coefficient values from? And at the end of the day, those coefficient values are derived from empirical experiments in which people actually measure things, and they derive the value of those coefficients. So that's kind of what I want to talk about today, is how we go about deriving those coefficient values. So there's a general process. Well, there are a couple names for it. One is curve fitting, the other is regression, because this is about really expressing the relationship of one variable as a function of another variable. So there are linear patterns, like relationships that are a straight line, where we use the simple form y equals mx plus b, and then there are a whole range of nonlinear ones. I happen to have y equals ax squared here, an exponential relationship, but there are many, many different forms, and all of our basic equations, they have different forms. Some of them are linear, but some of them are nonlinear. And so the question becomes, how do you go about, calculating values for these things? So curve fitting is basically just the statistical technique used to derive coefficient values for equations that expresses one value as a function of another value, that derives an equation that expresses those values. And like I say, linear regression just happens to be the subset of curve fitting in which we're fitting a straight line to data. And if you've taken any basic statistics course, you've no doubt spent some time, talking about linear regression and maybe even programming linear regression. So that's something that most of you have at least some experience with in previous classes. So that's a straight line. But like I say, in many situations, the relationships of interest are nonlinear. So for instance, we were just talking about the hyperbolic saturation equation. That's an example of a nonlinear equation. The relationship between the rate of reaction and the amount of stuff, the light, energy, nutrients, whatever, driving that reaction is nonlinear. It saturates at some point. More of the stuff doesn't give you more of the stuff. Or in this particular case shown here, it's an exponential function where more of the stuff leads to even more of the stuff, even a faster reaction. So, the basic essence of curve fitting is basically we're trying to derive coefficient values from empirical data for use in models. So we've collected a bunch of data on some phenomena, and we're trying to come up with coefficient values, more or less, that express one variable as a function of another variable. So in linear regression, we're trying to, we've observed a relationship in which some variable is exhibiting a linear response to some other variable. And so what we're interested in doing with regression is calculating the value of the slope of that line and the y-intercept of that line. So the m and the b in that equation. And in this particular exponential equation, we're interested in coming up with, if we know that this is an exponential relationship, we're interested in coming up with what's the value that gets multiplied by the x squared in order to come up with that relationship. So that's more or less what we're doing. We're trying to come up with these parameter values for something. And like I say, every equation we've dealt with so far has had various different coefficients or parameter values that I've just given you. I mean, it's just been part of the assignment. I've said, assume that the coefficient is this, and you've just done that. But this is about where those come from. Now, I want to take just a moment to say that part of the reason we just did the exercise we did, where we were sort of thinking about, okay, here's a phenomena, what's the basic formulation that might make sense in this phenomena, is that where possible, we want to use our kind of mechanistic or theoretical understanding of the relationship between variables to be our guide in choosing the equations that we're using. So if we understand we've got a situation that has the capacity to saturate, that's kind of like a hyperbolic saturation or Michaelis-Menten situation, well, that's the equation we want to be using. So when I say theoretical here, what I'm saying here is wherever possible, we want to use equations that we know make sense because of the nature of the relationships between these things. So if we understand a situation to be saturating, and there's a reason why it should saturate, there's a mechanistic reason why it should saturate. For instance, there's a factory, it's producing widgets. It has a maximum number of widgets it can produce because of just the equipment they have available. You can put more parts into it and they'll increase their production rate. You could put more parts and people into the plant and they'll increase their production rate. But at some point, the machinery itself is not capable of producing stuff any faster than some maximum rate. And so it saturates at some level. So if we understood that going in, then we would actively choose Michaelis-Menten as an equation for that. That would be, when we're talking about a theoretical relationship, we're talking about a situation in which we understand why a given equation might make sense. We've got a reason for choosing a given equation. There are, however, situations where we just don't have any understanding about what the relationship might be. And so in that case, we might be less interested in the equation embodying some sort of theoretical understanding of what's going on. We might simply be interested in producing an equation that best fits the data without really caring whether there's some sort of rationale behind that equation. So in this case, we're trying to answer the question of how one variable relates to another, but we don't really care if that equation meshes with some understanding of why it's a good relationship. And so whether we're sort of looking for a theoretical or an empirical equation really depends on our end uses. If we're interested in theory, if we're trying to understand and trying to use our understanding to describe the relationship between things, generally we want to be working with an empirical basis of our equations. And so, for instance, for your modeling projects, I really do want you to think about the basic formulations we've worked with this semester as analog. So which one of those actually is most similar to your situation and therefore is the logical sort of rational model to use, as opposed to saying, this looks like this. I think this has the same shape as that. So we'll just use this because it has the same shape. So we're really seeking sort of an underlying meaning to the equations we're choosing. We want to choose equations that are for mechanistic reasons. They make sense out of, they make sense to use. We're not just arbitrarily choosing them because they seem to do the right thing. But there are situations where, at least for parts of our model, we might not care that much about the why. We might just want it to do what it does. And just as an example of that, when I had you guys do models of photosynthesis as a function of light energy and created a day, but with that sine wave function, it's an example of that's not exactly how light works and reaches the Earth, but really the purpose of the model was to focus on the impact of solar energy and changing solar energy over the course of the day on photosynthesis. And we needed to drive that model with something that approximated the way sunlight falls on the Earth. And so it's not as though that little sine wave equation we created to model sunlight was central to our goal in the model. It was necessary to sort of drive our model and produce something that was kind of like what a day does, but we weren't really interested in modeling the solar system. We were simply interested in modeling variability in sunlight over the course of the day. So because we were focused on the photosynthesis side of the model and not on reproducing how the solar system works and how sunlight's delivered to the Earth, it was fine to just use that truncated sine wave function. Does that make sense? So in that case, the central piece of that model was the Michaelis-Menten relationship of photosynthesis versus light energy and exploring that as a model. And peripherally, we had to drive that model with an equation, and we didn't care so much about that because its only function was to drive the photosynthesis part of the model. So that's just an example of a situation in which that overall model combined an empirical relationship, Michaelis-Menten response of plants to variability in light energy, and a more kind of a theoretical relationship. That's what I meant to just say if I said empirical, but a theoretical relationship between sunlight and plant saturating on sunlight, differences in their half saturation constant. So all of those being very mechanistic and theoretical. And then just, we got to drive it with some outside light. So we'll just create this sine wave and it'll do its thing. Anyway, important to understand as much as possible in your models, since you're trying to develop modeling projects that have meaning, you should really be seeking theoretical, at least at the center of your model. You might, again, like that sunlight one, be wanting to drive it with something that is just empirical, but the center of your model should be theoretical. You should have a good rationale for why are you choosing the equations you're choosing? How do they fit? But just to talk about a little bit about empirical models, you can, through pretty sophisticated curve fitting, you can basically fit an equation to almost any line. So here's an example of some data. And there is actually an equation that will fit that data as this does. It's not a theoretical equation. That's actually an example of a very sophisticated kind of curve fitting called Fourier analysis, where Fourier analysis allows you to fit a function to almost any shape. You can take almost any set of data and fit a line to them, but it's not necessarily a very mechanistically, satisfying explanation. So empirical models, equations can be used to fit almost any data that you have. So in some cases, we use polynomials. Those are often good for fitting things. A polynomial is just an equation in which you express a dependent variable y as a function of a series of coefficients raised to higher and higher powers. And if you look at this, actually, the first part of this polynomial equation is just a constant. So if you cut everything else off, this is a constant. So y equals some constant value. If you shift over to this, you're just seeing the slope of a straight line, right? And then if you shift over further, you're adding in exponent, single exponent. on top of that line. And if you add in this, you're just adding more exponents. And so that has a straight line in it. If A2, A3, A4 onwards are all 0, then that's the equation of a straight line. And if A1 on up are 0, then it's just the equation of a constant. So it's got kind of built into it, you know, simpler stuff. It's got a straight line built into it, but depending on how many terms you have there, you can actually get that to do some pretty sophisticated curve fitting. And then, as I mentioned, Fourier analysis is a technique that modelers use to fit very complex data that has wave-like patterns in it. So that's an example of data that has waves in it. And by fitting a series of sines and cosine, so basically that curve is approximated by adding together a bunch of coefficients multiplied times sines and cosines. So you can approximate that by adding together a bunch of waveforms. And it's not critical that you understand this for this course, but I'm just saying you can get really sophisticated with your empirical modeling and basically take almost any data set, fit a curve to it, if that's your goal. Like I say, in this class, ideally we're looking for theoretical relationships. That's our real goal, is to use these basic principles that we've discussed up to this point in the course, use these basic formulations as analogs for the things we're trying to model. So trying to say, is this kind of a gradient phenomena? Is this a saturating phenomena? Is this a mass action phenomena? Let's choose those relationships if we can. So based on our kind of mechanistic understanding of what is the appropriate analog for what we're doing. And then we can use statistical methods, which we'll start to get into in a moment, for fitting stuff to those. But for empirical relationships, if all we care about is fitting a curve to it, then we can start by just plotting the data and then essentially just trying to find an equation that matches the data. And sometimes many different equations can match a given data set. And we use statistical procedures for doing that. Okay, so practical order of operations. We're almost always going to, once we've sort of thought through the theoretical part of it, we're almost always going to want to plot our data, look at our data. We want to have the independent variable on the x-axis and the dependent variable on the x-axis. So cause and effect on those two axes. And then we kind of want to look at it and look at the shape and try to figure out, is it a linear relationship? Are there max? Are there minimum? Inflection points? Are there data that are outliers in that particular data set? And then select an equation. Again, ideally based on our theoretical understanding of the relationship between the two variables. But oftentimes we can choose different things. And there's a great table that I have reproduced in the sort of exercise sheet for today that shows you the huge number of different shapes you can get out of essentially basic formulations. But, once you've sort of decided on an equation, there's kind of a standard approach for curve fitting. And that is what we're essentially trying to do when we fit an equation to a set of data is we're trying, and you guys know this from early on probably in school, where you were asked to fit a best line to data, and you're sort of asked to draw a line through there. Well, essentially what you're trying to do is minimize the distance between your points and whatever the line representing the equation that you fit to this is. You're trying to minimize the what's called the observed. So this is an observed value. All these points are observed values. You're trying to minimize the distance between your observed points and the predicted points. The predicted points being what your equation would predict if you were using your equation for a point. So that's your overall goal, is to minimize the difference between y observed and y predicted. And the difference between those, like the difference between your observed and your predicted, is called a residual. Some of you will remember that from statistics courses. But if you subtract your predicted from your observed, you're getting a residual, and we're trying to minimize the residuals in any sort of a curve fitting operation that we undertake. That's our goal. Now, in statistics, how many of you have had stats? Some stats course. Okay, some statistics. You guys don't really want to admit it, but you've had some statistics. In statistics, we kind of use this as a measure of goodness of fit. We often use something called the sum of the squares of the residuals. Maybe that'll ring a bell with at least some of you. SS residuals is what we refer to it as. And basically, it's just a way of measuring the overall goodness of fit of a relationship. So if you take every single difference between every single residual for every point in here, and you basically square those and add them all up, the number you get is basically it's basically how poorly your line fit. If all of your data fell exactly on your predicted line, if it was a perfect relationship, the sum of the squares of your residual would be 0. You would have no residuals, and so when you added them all up, they would be 0. So in general, when we're trying to curve fit, when we're trying to fit data to us, when we're trying to fit an equation to a set of data, our goal is to minimize the sum of the square of the residuals. We're trying to just make that as small as possible. And I'll just mention, the point of squaring it here is really just to get rid of the negative sign in this. So the squaring, don't let yourself get distracted by the fact you're squaring it. It's just a way of giving the same value to something that is above the line to a point that's below the line. So that's why we square the things. You could in fact use absolute value, and you could use absolute value as a statistical approach, the sum of the absolute value of observed minus predicted, and you'd more or less get the same thing. I've actually tried that. It fits data just as well. But statisticians have settled on the sum of the squares of the residuals as an approach, and it works well. So regression analysis often is referred to as the least squared method. And the reason it's called the least squared method is you're trying to create the least sum of the square of the residuals. It's a procedure for deriving coefficient values that minimizes the sum of the square of the residuals. And I know for many of you, it's like, oh God, I had this in statistics and it was kind of a pain in the ass then. And I'm glazing over right now because I don't want to think about this. In a second, we'll build a little simple example of this, and I think it'll make a lot of intuitive sense why it works and how it works and how it can be applied, not just to linear regression, but to nonlinear regression. Now, in linear regression, there's this technique we use where we sort of divide by the number of points. And don't write this stuff down, because I honestly don't care that you remember this, and definitely don't write this down. This is the formula that statisticians can use for calculating the slope of a straight line and the intercept of a straight line. And it's a little mind-numbing to look at, and I definitely don't want you to write that down. But I'm just telling you, there are some basic formulas you can use for linear regression, and they'll allow you to calculate from your data. So this is a little data set here, and if we took this little data set here and we plugged it into these formulas here, it would allow us to calculate a slope and an intercept for that line. It gets a little bit more complicated with nonlinear regression, but the same overall goal is there. Our goal is so nonlinear regression, as I say, there are many equations that might fit the data, but the statistical method is basically still a least squared approach. And so all of that was kind of a preface to getting a little bit of hands-on experience with this. And essentially, what a computer is going to do when you ask a computer to do a nonlinear regression for you, which is what all of us will do because none of us are going to do this by hand. What a computer is going to do is it's going to use a least square. It's going to try to fit a line through the data, and it's going to use a least squared method that basically makes many guesses about coefficient values, and it's going to keep coefficient values that make that difference between the line and the points that you're fitting that line to as small as they can possibly be. And it uses like weird algorithms that have names like Gauss-Jordan elimination and things like that to do its minimization. But the neat thing is that most programs, even like Google Sheets and Excel, have built-in solver algorithms which can do these things for you. And so what I'd like to do now actually is to have you guys open, I call it AS7, but you will not turn this in. This is a class exercise. So if you go to the syllabus for the class and you click on today, actually you can get to it in a couple of ways, but let's click on today's, today's class. So if you click on curve fitting estimates, there's a couple files here that I want you to open. Hello, thank you. Taking a while to get me there. Flow. Okay, so curve fittings at the bottom here. I want you to open up curve fitting. So open up this file. I've already gotten it open, so I don't want to open it too. But then I also want you to open and then make a copy of this AS7 curve fitting data. Well, I happen to have both of those open, but once you open this, please make a copy of it so you're working on a copy of it and we're not all working on the same one. So make a copy of that for yourself. And then we're basically going to walk through the beginning of this curve fitting sheet here. So if you want to have this open on the side, it'll give you some hints on what we're doing, but I'm going to go ahead and walk you through this. Okay, I'm going to make a copy of this too, so I don't bugger up the original sheet. Make a copy, and I think I will drag that into a new window so I can have these both open. Is there a question? So there's a bunch of data in here. Some of it comes from the Keenan Spain book. Some of it comes from actually data that students in past classes have contributed. And I want to start this process by clicking on the student data tab on the bottom and click on a contribution I made to this many years ago. So the very bottom data set says Peterson 88, and it says mass of Lily during her first 4 months. So this is my daughter's weight, and I think I mentioned this in class before. She was premature, so her parents were a little bit obsessed with, was she gaining weight or stuff, and so we set up this this fish scale in the kitchen, and would hang her little basket, her little basket on it with her in it, and weighed her sometimes multiple times a day, even just to sort of see how she was doing, track her weight, just the kind of things new parents sometimes do with their kids, just to see how she was doing. And this is the data. So this is real data from my daughter. Now, let me ask you this question. So here's a situation where you have some understanding of growth of human beings, right? What their pattern of growth looks like. And I'm only graphing, let's see, we have data going up to 123 days of her existence as a baby. What would you expect just from like first principles when you're thinking about growth of of a young child, what would you expect from your own knowledge of what would be a reasonable expectation for how a child might grow during 120 days of life? Yes.
Will grow quickly at first, slow down maybe.
They'll grow quickly at first and then slow down, maybe. I like the baby at the end. At the end too. Yeah, go. Right.
120 days, they might still be operating speed versus like a year down the road.
Right. Right. So what you're, and this is actually a really important thing you're doing, Francis, is you're thinking that the relationship between two variables may have one pattern over one time scale and a different pattern over a different time scale. And what I hear you struggling with is, this is a short enough, I'm trying to, because I hear you in part saying, well, they're gonna reach some, or at least I'm trying to think about your thinking here. And I'm thinking that you're thinking, I know they're going to achieve some maximum size at some point, and then they're going to flatten out. I also probably know that, during different stages of childhood, obviously there's an adolescent growth spurt. We're way the heck before that. So that's not a thing here. And so kind of what I hear you struggling with your brain here at this point is, I'm not sure whether this is linear or not. It might be a short enough time period that it's just plain linear, right? And generally speaking with these sorts of things, you want to assume the first things first. So it seems reasonable to say over some relatively short period of time, a kid might exhibit linear growth. So the point being, we want to think about the nature of a relationship before we even consider what sort of model might be appropriate. But we're beginning to think like, well, maybe an exponential could be valid, but maybe a linear could be valid. So we have an idea, as we know they might grow more quickly over time, but we also know that maybe this is a short enough time period that they're linear. So we've thought through those things. And that's what you want to do first. And then it's perfectly fair to say, okay, we've thought about it. We have some mechanistic ideas, could be linear. Maybe there's some exponential to it, probably not saturating yet because they're, it's only 120 days. But at that point, it's cool to go ahead and graph data. So what I want you to do next is go ahead and graph these data. So I'm selecting, and by the way, I'm ignoring the first column, which is actual time, because the second column calculates days since birth, which just is kind of like a more sensible and rational thing to graph it against the date. So those are the real dates, but it's easier to interpret looking at days since birth. So I have both of those selected. And, I'm just going to go in and insert a chart. Right? Everyone with me? And when I insert the chart, that's going to do nothing. When I insert the chart, it's inserting a line chart. I don't actually want a line chart. A line chart, we want a scatter chart. I don't even want to talk about why we don't want a line chart, but we don't want a line chart. We want a scatter chart. So under chart type, I'm going to click on that and I'm going to scroll down to something that just gives me the individual points. It's not connecting the point. So I'm going to click on this scatter plot here. And that's showing me each actual data point that I measured. And you can see there sometimes when there's a lot more data. Towards the end, we were measuring weight a lot less often. So you can see that the frequency of data collection changed over time. And if we were looking at this, if we were to look at this on a very short time scale, you would actually see oscillations in weight depending on the last time the kid either pooped or puked, which kids do a lot of when they're young. So what's going in, or whether they've recently fed for that matter. So their weight goes up and down depending on what's immediately coming in and what's immediately going out. But over the longer time, you're obviously seeing what actually looks like. What does this look like? Does this look exponential or does this look linear? Looks pretty linear. So we should feel pretty comfortable fitting a straight line to this. And as many of you have done in Excel or in Google Sheets or in other simple spreadsheet or even some simple statistical programs, you can easily put a line through that. And so I'm going to go ahead and click on customize, and let's see. I want to Where is it? Is it under series? I'm trying to figure out where I add my line. Yeah.
Under series. there's the-
Under series. Right. Under series, I want to choose, wait, where are you seeing that add trend line?
It's right above legends on your screen. You go exactly the width that your mouse is at.
Right. I want to add a trend line. And once I've said add a trend line, I want to choose linear, which is the default one. It can actually fit other equations. We talked about a polynomial equation. So we could select polynomial, but we've just said we think it looks linear. We'd already had a discussion that a line makes some sense there. And we also want to, it has the capacity to add a label, and for some reason this is where it would put the equation. So you want to put under label use equation, and then you also want it to show the R² value. So it's basically doing a regression here right now. So that sort of least squared process we talked about, it just did that least squared process there in fitting these data. So that is the slope of the line. It's 0.00251. And that is the slope. So that's how much kilograms per day she's increasing in weight. So that's kilograms per day multiplied times day, which is the X value, plus a Y-intercept, which is presumably something near her birth value, her weight at birth, 2.01. So that's what those values are. The 2.01 is an estimate of what she was at time 0 when she was born, and the 0.0251 is basically kilograms per day, and then X is days. So add those together, and I'm going to get her weight. And the R², all of you have obviously seen R² and know that a high R² value means that it's a good fit on the equation, but you can actually directly interpret the meaning of R². R² can be interpreted as the percentage of variability in my dependent variable, in this case, weight, that is attributable to my independent variable, in this case, time. So in other words, that R² of 0.99 means I'm explaining 99% of the variability in her mass by knowing how old she is. So it just means it's a very strong relationship. I've got a lot of predictive power in this particular model. This equation, this linear equation, this model is a very, very good, strong relationship. So, yeah. So this is a linear process. I kind of want to show you though what's going on behind the scenes with the way this is being calculated, because what's going on behind the scenes can be directly converted into be directly used to understand what goes on with nonlinear curve fitting. So this is a straight line. In fact, that ugly equation that I said you don't need to remember, this equation that had all the summations and stuff in it, is basically what's going on in the background for this value to be calculated here, this slope and Y-intercept and R² value to be calculated. But what I want to do is to give you a sense of that predicted and observed. So what I'm going to ask you to do is to insert a couple of rows between the title of this and the labels that are above the data. So I'm inserting a couple rows here so I can write my equation. So my equation in this case is it's a generic equation of line y equals mx plus b. Okay, so that's the equation of a straight line. This is a straight line. And what I'm saying here is that what we're trying to derive is values of m. So m equals, I'm typing underneath that, and b equals, to make a little bit more sense as I go further. But basically what I'm trying to show you now is how you would curve fit. Yeah, it's good. Everyone good? Everyone with me right now? Okay, I'm gonna make my screen a little bit bigger so you guys can do this a little better. Okay, so now, like I say, this is my observed value. This is the weight we observe. And what we want to do here is create a y predicted. So I'll call it y dash pred. So this is predicted from my equation. Now I happen to already have an equation here because it already fit things, but I'm gonna pretend that I don't know what this is, and I'm gonna just start off and say, well, maybe slope is equal to 1 and y-intercept is equal to 1. So I'm gonna start with those as my predictions, because let's say I'm just starting this process and I have no idea what the slope or the y-intercept might be. So I'm just throwing out kind of random guesses about what my slope and my intercept might be. Yes.
Do you need the ones in the same box or not? That's what M equals.
No, this is just a label. This is just so you know what these things are. No, I actually want them in different boxes because I need to use them in the equation. So basically what I'm going to type in here is my slope equation. So I'm going to say this equals M, so this number 1, equals, yeah, right, M, that's good, actually, I shouldn't have said oops there, times X, which is how old Lily is, so clicking on that, plus what I have is a B value here, right? So all I'm doing is making this the equation, the prediction. So it's M, it's the value I have for M times time plus B. Now, in this case, as we did the last time we were messing with Excel when we were doing our numerical integration, we need to put dollar signs in front of these fixed constant values, because otherwise it's going to make a mess when we copy the cell down. So I could put dollar signs in front of both B and 152 and 153, but I could also not put it in front of B because I'm just going to copy it downward. You guys with me? Yes? Say no if you want me to slow down. Because what I'm going to do now is basically copy that cell downwards. And so I'm going to have a predicted value for all of these things. And you can see that this is a terrible prediction of her weight. It says she should weigh 124 kilograms at day 123, and she only weighs 5. This is dreadful, just a terrible, terrible prediction. And that's because we started with these really arbitrary values here. That's okay. That's just fine. What we're going to do now is we're going to put in here the predicted minus observed. So y pred minus observed minus y observed. Okay, and y dash observed, sorry, not y equals observed. Y pred minus y, I'll get rid of that little dash there because that's confusing. Doesn't matter what you call it exactly, but the bottom line is what we want here is to subtract our predicted from our observed. And so this is going to be equal to our predicted value minus our observed value. And I'm going to say, go ahead, yes, autofill, that's fine. So this is all of our predicted minus our observed. Now, we could do this in one equation, or we could do it in two. Let's do it in two. Let's call this y pred minus y observed. And I'm going to put these in the parentheses and then put hat squared because we're going to square that value. So we're doing exactly the procedure that I talked about. We're going to take this value equals this value. And I can do hat 2, and that means squared. So I'm just taking that. I could have done it in one column. It really doesn't make much difference. So I've got a predicted value, predicted minus observed, and predicted minus observed squared. I want to make sure everyone's with me on this. You guys with me? Tell me no. You good, Mads?
Yeah.
Okay, cool. Okay, so this is now adding those up, and oops, I'm going to copy this one down. You may have already done that. Yeah, if anyone's not with us, slow us down. We can do that. And then at the Francis, you good? Okay. So at the bottom of this, let's call this one SS res, and that's going to equal to the sum of equals sum, and then I'm going to just include all of the cells above it that are in this. So this is the sum of the square of the residuals. Again, I'm doing exactly what we talked about. If I click on that, you can see I've added up all of the squared residuals, and that's the sum of the squares of the residuals. You good, Justin? You okay? Yes. Okay. Francis, you good?
Yeah.
Okay. So this is like this is an enormous number because our equation is fitting this really poorly. And let's do this. Let's actually nuke this. Let's delete that graph, and let's now graph these first 3. Well, we're graphing days, and we're graphing mass and y predicted. So we'll graph those 3 together. So we're going to this is our fit again with funky parameter values, but we're going to insert a chart, and once again we're going to not choose their default one. We're going to choose scatter. Why am I not seeing scatter here? Yellow. Okay, column type. So we want type, and we want to choose scatter again. Okay, and so hopefully you have a graph that looks like that, which is again pretty dreadful as a fit here. So this is our fit line, and this is our actual data. And what I want you to do now is I deleted my other graph, so I can't. I mean, I do kind of vaguely remember what it was. But what I want to do, I'm actually going to drag this graph up a little bit so that it's closer to where my that's closer to where my coefficient values are. So I can look at my coefficient values while I look at my graph. Very touchy. Okay, maybe I'll close this box too, so I don't need to look at that. Right. So now what I can do is I could by eye change these values and see how they change this thing. So looks like my y-intercept is way too high. Maybe I'll make that like 0.1 and see how that does. That still looks terrible. Y predicted, huh? What's that? Well, let's do that too. Let's make this 0.1 and see what happens. I'm gonna say, why don't you guys see? Like you guys actually might still remember what the values were, but you can see I'm getting it much better right now. It looks like my it looks like my slope is still too high here. So I probably want to reduce that a bit. 0.01, let's see what that does. That messes this whole thing up. I'm going to give you a minute to play with these values. And this is like a little, we're doing a little fun contest here because I want to see who can mess with those values and get the lowest sum of the square of the residuals. So right now I have a pretty terrible sum of the square of the residuals. It's 380, but it's a heck of a lot better than it was. You got 1 minute to play with those values and see what you can get as the lowest sum of the square of the residuals for those. So just play with those two values, the M and the B, because this is essentially what, at least for nonlinear regression, what the program would be doing. It would be playing with those values. It would be using algorithms to play with those values to minimize the sum of the square of the residuals. I'm going to actually move my sum of square residuals to the top so it's easier to look at both at the same time. All right, how are people doing? What's your sum of the square of the residuals?
0.22.
0.22. Okay. Anyone do better than that? What'd you do? 0.14. Okay. Right. So you guys can play with this. And like I say, that's kind of what Excel or any statistical program might do. There are tools to do this. And so what I actually want you to do now is go up to extensions and then go to add-in and get add-in. Because this doesn't necessarily come installed on actually it doesn't come installed on Excel either. You have to add a solver and you want to look for solver and then type return and you want to install, I already have it installed so it says checked on mine, solver optimized for Google Sheets. Everyone with me? Yes. Or are you there? You got it installed. Okay, great. So go ahead and install the thing. And then once you've installed it, that should then show up under extensions. And so you want to go down to solver in extensions and click start. And it will open a box on the right, which allows you to optimize this thing. And what you want to minimize is wherever your sum of the square of residuals is, that's the number you have in here. And I don't know how it's this smart, but it seems to already know that I want to minimize that. Does it know you guys want to minimize that too? That is really almost scary that it knows that you want to minimize that. I don't know how it knows that because that's creepy almost. And it has M and B in here, which is really also kind of spooky because it doesn't know what M and B are. So does yours have M and B in it too? That's some weird stuff because there's nothing actually named M and B in here. And that's not actually what you want. What you want though is you want to change this number and this number. So actually what you want to change is B152, comma, and B153. And we're not going to subject it to anything else. But it's going to then basically mess with those values to make that value as small as it can be. And I didn't tell it to solve, but it seems to have already wanted to start doing that. So ultimately, there are some different algorithms you could use to do that, but you're just going to click solve. And then it's going to go out there and try to make F152 as small as it can by messing with those two numbers there. So hopefully it just did that for you.
Where did it put that?
It put it in the cells because I said I wanted it to minimize. So you can see my B152 and 153 are now, it changed those cells. Did you put B152 and 153 in here? Comma B152, comma B153.
I have an extra line.
Is it working now? It's thinking about it. Yeah, but like I say, what it just did is it just went out there and tried lots of different things and said, okay, I played with this a whole lot, and I've gotten like I've gotten the sum of the square of residuals to 1.92, which is as low as I can get it, 0.1129. What did you have before?
0.025 and 2.
No, but I mean for your sum of the square of residuals before we started this.
Oh, 1.4.
Well, that's pretty good. You were pretty darn close to begin with. But you may have remembered what it had up here. It basically did that in the previous one, right? So the values that it had in there, these values should be, I can't remember exactly what we had on our original regression. I don't know if someone still has that graph, but that M and B should be darn close to what it calculated as its slope and its intercept. Does anyone still have that original graph, or did everyone delete it? We could actually, yeah, it doesn't matter. The numbers are really close. Everyone, I know Mads is having an issue here, but is everyone else good? Yes? Sadie, you good?
Mine's still not downloading solver.
Oh, the solver isn't downloading.
Yeah, we're gonna technical issues.
Okay. You guys are both good, Ari? All right, what I want to do now is show you, okay, so we just did a linear thing. Like I say, you could have just asked a cell to do that, but what if you have a nonlinear equation that's not built into Google Sheet Brain? Let's go over to this first sheet, first worksheet, KNS curve fitting data. And I want you to imagine that these data, I'm inserting a couple lines above, insert row above, insert row above. So I have inserted 3 rows between these data and this. And I'm just going to tell you these data here, let's imagine that these are nutrient uptake. So it's the rate of growth. Imagine that Y is the rate of growth, and X is the amount of nitrogen in the soil. So it's plant growth as a function of nitrogen concentration. So you've grown plants at a bunch of different nitrogen concentrations, and you've seen how fast they grew. Let's imagine that's what these data are. If I'm saying we're graphing plant growth versus nutrient concentration from a mechanistic perspective, what would you anticipate as a shape of a relationship there? As I add more nitrogen, what's going to happen to plant growth? Yes? Hyperbolic saturation would be a reasonable thing to think of there, because eventually nitrogen's not going to be limiting, and adding more nitrogen is not going to add more plant growth. So I'm saying, let's imagine that's where these data are from. And what that means is we want to use a model that is a hyperbolic saturation model. So let's go ahead and put the equation for hyperbolic saturation in here. So I would be writing Y equals, help me out, what would I write here? So this is sort of like a little quiz here. What would be the right equation for hyperbolic saturation if I'm calling my independent variable X, my nutrient concentration is X, and my growth rate is Y. Y equals what? Just give me an equation here. That is the hyperbolic saturation equation. So this is basically, what is the hyperbolic saturation equation? Y equals Y max, good, yep, times X divided by X plus, let's call it, it's a half saturation constant. We can call it, we'll call it K. We'll just call it K. That's fine. Okay, so what I typed in there, just based on what Ari just said to me, is Y equals Y max times X divided by X plus K. So that's the equation I'm trying to fit to this. And my parameters here, the things I'm trying to solve for, or what? What are the terms that I want to solve for here? From this data, I want to figure out my coefficients. What are my coefficients? What are the coefficients in here? Y max and K. Okay, so I could say Y max equals and K equals. Okay, and again, I could just start by saying, let's make them both equal to 1, just because I need some starting place, some random starting place. So I'll just say that. And then I'm basically, let's just verify this though. Let's go ahead and graph this XY data so we can take a peek at what it actually looked like and make sure that our assumptions about data are good. So I'm going to close my solver and insert a chart. And yeah, that looks like a hyperbolic saturation relationship. So I feel comfortable fitting a hyperbolic saturation relationship to that. So I'm gonna nuke that graph for a second, just because I don't want it in my way. And okay, so now I'm going to again say, this is my Y predicted, Y pred, and this is Y pred minus Y observed. And maybe I'll just square this whole thing here so that I do it in just one. This is going to be my my residual squared. Can you guys see what I'm doing here? Okay. I'm just putting a title on this for now. So this is my predicted, and this is my predicted squared, my predicted minus observed squared. And so in this Y predicted, this is where I'm going to sort of type in the equivalent of this equation. So it equals to Y max. So I'm going to click on Y max times the quantity, the value of X divided by quantity, the value of X plus K. Just make sure everyone's with me on this before I go ahead. All I did was to type in the sort of Excel equivalent of the formula in A6. That's with me? Mads, you okay?
Yeah, does it matter that you're missing a parentheses?
It does, actually. It'll have a heart attack if I try doing that. So I should put that parenthesis in there. And the other thing I'm missing is what? What haven't I done yet? Dollar sign. So I got to put dollar signs in there too. To hold those things that are, wait, no, that's not where I want a dollar sign. That doesn't want a dollar sign. I want it in my constants. And my constants are Y max and K. So I only want the dollar signs for Y max and K. And like I said, I could put a dollar sign in front of the B's, but it's really the numerical reference that I want to hold constant. So I'll just put those dollar signs in. So people with me? Justin? Yeah, okay, cool. Yeah, okay, cool. So it auto-filled for me. I don't know. Oh, and then it un-auto-filled. I guess I needed to click yes on that, but whatever. I'll drag it down. And maybe because I don't want to look at those horrendous digits, I'm going to shrink down the numbers a bit. Oops, too much. All right. So I have less digits, just so I don't need to look at so many digits. Okay, now I'm going to do y predicted minus observed here. So this equals predicted minus observed. And like I say, I'm just going to, in one fell swoop, also square that difference. So I'm going to put on a square there. So guys, good?
I'm a little confused as to why you're squaring it, and I know that it's like to get rid of the negative, but it also significantly changes the value.
Yeah, it makes it giant because I'm squaring the damn thing. And I will just say this to you, Mads. I'm not a statistician, and I can't really answer your question because I have wondered that. And as I sort of mentioned in passing the other day, to me, it makes more sense to just take the absolute value of the darn thing. And I have tried taking the absolute value and using solver with the sum of the absolute value instead of the sum of the squares. And you get exactly the same answer as you do if you do the sum of the squares. So I don't know why statisticians use the sum of the squares instead of using like the absolute value. I can't answer that question. It doesn't actually give you a different answer, but I am darn sure that there are statisticians in the world who could give you a very good explanation of why they're squaring it. But I am not one of those statisticians. So I don't know. Someone does know. Did someone just say they knew? Okay, well, if anyone knows, you can share it. But I'm just saying, is a way to get rid of negative value. And at the end of the day, you're adding up the sum of them. And whether you're adding up the sum of the squares or whether you're adding up the absolute value of the residuals, the sum of the absolute value of the residuals, you're going to get a number that you want to minimize, you know? Either way, you're trying to minimize that value. So we're going to, again, at the bottom here, put SS res, and that's going to equal the sum of all these residuals. And wow, this thing is so smart, it knows what to put in there. I tell you, they must have like, they must be using like, oh no, they're not. They're adding up a bunch of cells I don't want in there. They're not as smart as I was giving them credit for, but they are crafty, these, whatever this artificial intelligence is behind Google Sheet, because they're like the way they put M and B in that other one, that's like spooky to me. Like, where did that come from? You know what I'm saying? All right. So this is what we're trying to minimize here. And obviously we're doing a terrible job here. Let's go ahead and graph these things as we did the others and see what our insert chart. It's really arbitrary, like what it chooses to graph spontaneously. Oh, why is it not letting me choose scatter plot, which is what I want here? Okay. Check this down a little bit. I can't see what I'm looking at here. Are you guys more or less with me here? That's good. You're doing very well. What are you whispering? Huh? We are just doing a dreadful job here of fitting. You notice that? Our line is terrible. All right, you guys have 1 minute to guess values of Y max and R. And you should be able to do that because like presumably Y max is someplace up here. You should be able to use your intuition. So, okay, we got a minute See who gets the best, who minimizes SS residuals the most. All right, we're going to stop there. All right, how'd people do? Who wants to, who's got an, I've got 92.6. Is anyone better than me? All right, what do you got? 14. Damn. Anyone better than 14? What are you, Ari? 0.87? Oh my God, we've got a human calculator here. Well, you were much more efficient than the rest of us. Now, let us use the process we just used, because this is like, we wouldn't want to guess these things. We want to go to the solver. And so let's go up to extension solver. And start, and it's exactly the same procedure we're using here. We are choosing, and let's see if it's trying to, let's see if it's smart enough to know what we want to minimize. It's saying E22. E22, I want to minimize E22. How did it even come in the ballpark though? I just don't get that. Minimizing B7 and B8. How does it know that? That is just, to me, super spooky. Yeah, there's someone at Google is like really creeping out here. Okay. Is everyone on this one? You solving? I know, Sadie, you're having some issues here with Google. Is that true? Have you solved your Google issues, or are you still struggling with Google? Okay. Interesting. What did you get before, Ari? But what did you get for your sum of your square of residuals?
I have a different number if you want. I have got 0.85. Yeah, I think yours is rounding.
Oh, interesting. I don't know why I'm not getting it quite right here, but the principle is what it is. It's so we're getting different values. I mean, mine look like they're spot on. I can barely see the difference between the blue's like slightly overlapping. Yeah. That seems weird to me that it is using my truncation. That just seems strange that it would do that. But I think you're probably right in a weird way that it must be. I wouldn't think that it would do that. I would think that that was just like what it was choosing to display. But I think you're probably right. It has to do with like how many I put in there.
See, when I did, because I did that originally too, after you did it, and I just fixed it and it changed mine to 0.8505.
Yeah, it just did that. It just did that for me too. So I find that very strange, but that is what it is. And anyway, that's the process. Now you could do that with any particular equation, that kind of curve fitting. So we happen to have just tried it on hyperbolic saturation as well as linear, but you get the idea. This is how we derive coefficient values, is through this this process. And yeah, that's very satisfying. It just added it now, or?
So I got it to add, and then when I solved, it was like great. And I finally got it.
Well, that's good. That's gratifying. Just in the nick of time. Well, it may have been frustrating, but you got it working. All right, Ari, we're bailing right now.
Yeah, so I'm in class, so I'm like